In section 7.3, we really start to tie all of the ideas in this class together with a nice little bow and slap it into the tree for Christmas. So what I want to do is I want to motivate section 7.3. 7.3 is a technique called diagonalization, and in this video, I'm not going to show you how to compute anything. I'm just going to show you some ideas here. So let's get started. Consider the first order linear system. So what we're now talking about is first order, meaning differential equations. These are all derivatives here on the left side, and they're all first order derivatives. They're all the first derivative. And it's also a linear system in that these differential equations are linear, and that there are no powers or products of the derivatives and their unknown functions. But this particular one has some issues with it. So let's talk about what that issue is, or those issues. The first thing that we want to note here is this is difficult to solve, not just because it's a differential equation, difficult to solve as this system is what's called coupled. That is to say, each equation we have here, this one is in terms of x1, the derivative of x1 doesn't just depend upon x1, but actually depends upon some other unknowns. I don't know what x2 or x3 is, and so what we're doing here is we're assuming that each of these unknowns, x1 is a function of t, x2 is a function of t, and x3 is a function of t, and these are all unknown to us. Now, that's notoriously difficult to solve because I simply do not know what these other functions are. That is to say, if I give you something like dy over dt is equal to, or maybe I shouldn't use y, maybe I should use a different letter, right? Some classic stuff. What if I said find f of t if df over dt is equal to f of t plus g of t plus h of t, and I never told you what f and g were. It'd be one thing if this was just f, but it's something else completely when I have more unknown functions in here, and that's exactly what's going on here. Now, I am given some kind of clue as to what these other functions are by way of these other differential equations. This is a differential equation which tells me how the derivative of x2 is not only related to x2, but is also related to these other functions, and so on and so forth, right? Here, let me just highlight these while I got the same color going on here. And here I'm told some information about x3, how the derivative of x3 is related to x3, but I do it through a relationship involving x1 and x2. And so this is what we mean by coupled. That is to say, the derivative of each one of these functions depends upon more than just one unknown function, which is not something that we've dealt with before in chapter 1 when we were dealing with differential equations. Okay, so how can we begin to deal with something like this? Well, another thing that we should note, so this is note number 1. Let's make another note here. 2, we've been studying matrices and eigenvalues and eigenvectors and all kinds of stuff like that. And one thing we can do here is we can write what's called the vector formulation for this system. And indeed, we have done something like this in one of our earlier homeworks. And so what I can do is I can take this system here, and I can express it as x1 prime instead of dx over dt. We'll just write it as a prime. X2 prime, x3 prime, which in fact I can write as the derivative x1, x2, x3 of a vector, or I can simply write as x prime as the vector x prime, or maybe even write that as dx over dt, where here I've used the vector notation to show you that this has more than one component. That's the left side. The right side, and I'm just going to copy this here, this right side of this linear system, I can also rewrite in a certain way, right? This can be used, expressed as simple matrix arithmetic. This is the coefficients, 3, -2, -2, -3, -2, -6, and 3, 6, 10, right? Times that same vector x1, x2, x3, although here it's not the derivative. Up here it's the derivative. Over here it's just x vector. And I can express the right side as coefficient matrix times that same vector. And so what I can do is I can express this as x prime is equal to ax. And so while up here the entire system was coupled together, I can think of this as a macro single linear differential equation where I have x prime is equal to ax, and I'm really talking about, although I have multiple functions, I'm really talking about a single vector function now, and we're looking for the solution. So we've now expressed this differential equation system using matrices, and we can sort of solve it in a macro sense. Now the next thing I want to say here is, note number 3, in Calc 2, when you first deal with differential equations, and you don't even know you're dealing with differential equations, if I was to write something like this, dy over dx is equal to something like x squared e to the negative x cubed, most people don't even think of that as a differential equation. They really think of it as an integration problem. They say, well, the function is y equals x squared e to the negative x cubed, where we integrate with respect to x. So those are the same thing. It's very similar to what we're talking about here, in that we have the derivative of a function, although down here it's an actual function and up here it's a vector function. What I want to get at is this is also difficult to integrate, not actually, but it becomes easier to integrate if we do something clever, which is called a substitution. And so here we might do a couple of things, right? We might declare our substitution. So define your substitution, and we might do something like let w equal negative x cubed. And then the next thing that you would do after you do that, right, is you would take the derivative of your substitution. So we would differentiate, and we would get dw dx is equal to negative 3x squared. And then we would plug everything in, and we'd actually get an alternate form here. This would be negative 1/3 the integral of e to the w dw, and this is easier. And so I guess the question here is, that was supposed to be a Q. Hold on a second. I guess the question here is, can we do something similar with x prime equals ax? And the answer is, yeah, we can. So let's see what we're going to do. We're going to declare our substitution. So suppose S, n by n, is an invertible matrix. And we do something, I don't know what S is. Just like up here, I don't know what my W substitution is, and I let x vector equal S times y, where y is acting like my W, so to speak. So this is going to be my substitution. After I declare my substitution, the next thing we would do is differentiate, and we would simply have x prime here is equal to the derivative with respect to, I guess in this case, the underlying variable would be t, of sy, where S is just a coefficient matrix. Coefficient matrix. And we all know how coefficients work with derivatives. We can simply factor that out. And so we'll factor out our coefficient matrix, and we'll get the coefficient matrix S times the derivative with respect to t of y, which, oh, that looks sloppy here. Let me fix that. Which I could just write as sy prime. And so I can then use that substitution. If x prime is equal to a, x is my original system, and we substitute, I can substitute for, let's see, I can substitute for x prime, X prime is sy prime, so I'll rewrite that. This is sy vector prime, and that will be equal to, well, I have ax here, so let's see, a is not going to change. I don't know what to do about a, but I do know that I have a substitution. I declared what my substitution was going to be for x. X was s times y. So then I can rewrite this as S matrix y, or sy prime is equal to as y. Now, the other thing is we have assumed that when we chose our substitution, this is invertible, meaning S inverse exists. And so what we're going to do is we're going to multiply both sides by S inverse. I'm going to have S times y prime is equal to as times y. And I'm going to multiply correctly both sides by S inverse. And although I can't commute matrix multiplication, I can reassociate it so that this becomes S inverse S times y prime is equal to S inverse as times y. Now, this is then by default here the identity matrix. And I get I times y prime, and I'm just going to rewrite this as S inverse as times y, or y prime vector is S inverse as. Now, it looks fairly complicated, but the one thing I know for sure is everybody here is a square matrix. S is n by n, A is n by n, and S inverse is n by n. And an n by n matrix times an n by n matrix is another n by n matrix, and so it goes. And the result here is simply going to be, I don't know, some other n by n matrix. And we have changed the system, and you know, generically speaking, it doesn't actually look that different. It's very similar to what we started with, right? We started with x prime equals ax, but what have we done? We've switched out the x vector variable for a y vector variable, and we've changed the coefficient matrix a little bit. So how does that help us? Well, you know, back here when we're talking about calculus, you know, we're starting off with more or less an exponential function. And when we do the substitution, we're left with another exponential function. But the idea here was we did this substitution so that this was easier. And so the question then is, hopefully, we can, I guess this isn't a question, hopefully we can find S matrix such that S inverse AS equal to the B matrix makes Y prime equal to BY easier to solve than X prime equal to AX, right? That's the whole point of substitution. We're doing this trade out. Now, so here we go. Here's the question. What would make y prime equal to by easier? So that's the next question. Well, I'll tell you. I'm going to rewrite this as y prime equals dy, where b is some other matrix. I'm just changing the letter. Don't worry about that. But I'm making it d because I want this to be a diagonal matrix. Now, what does that mean? Well, suppose this is a diagonal matrix, i.e., once we do this substitution, y prime is equal to some kind of, in a 3 by 3 situation, let's just say a11, 0, 0, 0, a22, 0, 0, 0, a33 times y, for instance. So if we rewrite that, that means that y1 prime is equal to a11 times y1 Or here, let me start over here. Let me change the color. That red's getting hard to look at. That is, we're assuming that this is some kind of y1, y2, y3 prime is equal to a11, 0, 0, 0, a22, 0, 0, 0, a33 times y1, y2, y3, where the left side is the y vector. Sorry, the left side is the y vector prime, and the right side has the original y vector. And if we multiply that out and we set each entry in this matrix equal to the result over here, remember this is 3 by 3 times a 3 by 1, which the result is a 3 by 1, we're going to get y1 prime is equal to a11 y1 plus 0 y2s plus 0 y3s. And y2 prime is equal to 0 y1s plus a22 y2s plus 0 y3s. And y3 prime is equal to 0 y1 plus 0 y2 plus a33 y3. And this is, of course, fundamentally different than the system that we started with, being that this sucker's diagonal. And it is now what we call decoupled. That is to say, although I have y1, y2, and y3 in every equation, y1 prime no longer depends upon y2 and y3, and y2 prime no longer depends upon y1 and y3, and I'm not sure why I colored those in the way that I did. Hold on a second. Spaz. No, come on. This is 0 y1s and 0 y3s, and then 0 y1s and 0 y2s. And so in each case, I have decoupled the system in right across the board. y1 derivative now only depends upon y1, y2 derivative only depends upon y2, and y3's derivative only depends upon y3. That is to say, this is now three very separate, separable differential equations. That is to say, y1 prime is equal to a11 y1, y2 prime is equal to a22 y2, and y3 prime is equal to a33 y3. And each one of those can be solved very simply. Either you can look at that and say, I'm looking for a function such that when I take its derivative, I get back a constant multiple of the function I started with, or you can simply separate this. This is dy1 over dt is equal to a11 y1, and you can separate that and say dy1 over y1 is equal to a11 dt. You can integrate both sides here, and you're going to get the natural log of the absolute value of y1 is equal to a11t plus some constant. And you can solve for y1, and y1 is going to be some kind of ce to the a11t. And so very quickly here, what we're going to see is y1 is, let's call that c1 e to the a11t. Following in that manner, y2 will be equal to c2 a to the 22t, and y3 will be equal to c3 e to the 3 a to the 33t. Now, that is what the y vector is equal to. Now, just like when we do substitution, if I roll back up here and I talk about this calculus that we were doing, just like when we do substitution here, this is now easier to integrate. This is negative 1/3, and the antiderivative of e to the w is e to the w plus c. And then, of course, we didn't start with w, so now we want to undo our substitution. This is negative 1/3 e to the negative x cubed plus c, where we undo the substitution. And the same is true down here. That is, we started with x prime equals ax, but what did we just solve? We just solved y prime equals diagonal y. That's a poor color choice there. Hold on. We just solved y prime equals diagonal y. And so we have y, but we didn't start with y's. We want x, but we know x is s times y, which will be s times y1, y2, y3. And by performing this matrix multiplication, we are going to get the answer to this coupled differential linear system. And that's the process that we're going to go through. Now, it seems long-winded. It's actually pretty quick, and we're going to develop the technique to do this in the next couple of videos. So we're going to do a substitution. We're going to be clever about it, and when we're done, we're going to undo our substitution. Okay.